Okay. So before Lynn introduces our speaker, I just wanted to remind everyone of some guest speaker ground rules that we have. So during the presentation, please do not interrupt our speaker. Make sure you keep yourselves on mute. But if you do have a question, feel free to enter it into the chat, or you can hang on to it in your mind until the end, and then you can ask aloud by using the raise hand function when we have time for Q&A at the very end of our speaker. This will just let everybody, we have a lot of people here, so it'll help us all to get a chance to hear. And yeah, so I'll pass it over to Lynn to introduce our speaker.
Okay, well, I am super excited to introduce today's guest speaker, Dr. Michelle Kirchoff, who's going to tell us about impact cratering and bombardment of objects in the solar system. And Michelle has a BS in physics from the University of Missouri at St. Louis, a PhD in Earth and Planetary Science from Washington University, which is actually in St. Louis, despite the name, and currently works at the Southwest Research Institute. She also has a son on the spectrum and she loves puzzles. So there she is with her son, I guess, when he was younger, inside a big crater. Hopefully she'll tell us which one that is. So, okay, we will toss it over to Dr. Kirchoff now, and you should be able to share the screen.
All right, thank you. Can everybody hear me okay?
Yep.
Yeah, okay. Okay, so we're gonna see how this works.
And you all can turn your cameras off now if you are feeling uncomfortable, but it's okay to leave them on as well.
Would
So
it be all right if we just, oh, sorry.
That's okay. Can you see the presentation or do you still see like
We-
the application?
Yeah, we see that. We see the app. It's not in slideshow mode.
Okay, let me try this again. Ugh. Okay. I know there has to be a way to do this. Sorry, I haven't actually done this very frequently, so surprisingly. Let's try this again.
Okay, so yeah, start from beginning. That usually does it. Where it says slideshow up on the top. I thought you were up there, the top menu where it says slideshow. Yeah, there we go. Perfect.
There we go. Okay.
Yay. We did it.
All right.
All right.
Yay. Oh, sorry. I'm trying to now move the Zoom thing out of the way. Okay. Yeah. So I am Dr. Michelle Kirchoff. I work at Southwest Research Institute. As mentioned, we are in Boulder, Colorado. So if any of you come to school in Boulder, I get my contact info at the end, so please feel free to contact me. And I'm happy to be here giving this presentation on impact cratering or bombarding the solar system. So we'll start with a little bit of history and then we'll go into some research I've been working on. So like many things in space, it started with Galileo. In the 1600s, he was taking lots of telescopic observations and he saw these circular features on the moon, and he noticed also that they had to be depressions because of the way the shadows fell. And this is an actual picture from one of the books he published.
This slide did not advance.
It didn't.
Still showing the title slide.
How about now?
And we should be recording this. Megan, did you record this part?
Oh.
I believe the whole meeting is being recorded, so
Okay.
we should be okay.
Okay.
We're going.
Yeah. Okay. So hopefully you see the next slide.
Yes.
Yay. Okay. Yeah, for some reason the sharing paused for a second there. And so yeah, this is a picture that Galileo actually drew of what he saw of the moon through his telescope. But he ultimately made no speculation on the origin of the features. In the later 1600s, some people started thinking about these more and what they could be from. And since they looked similar to volcanoes, some people thought maybe volcanoes. But people had already been like dropping things into mud and sand and noticed that a depression was formed. So some people thought about impact, but the space was thought to be empty at that time, besides the Earth and the Sun and the Moon and some of the planets. So they thought, well, what would make these holes? What was actually doing the impacting? So a couple of centuries later, people got thinking about this, but it was really G.K. Gilbert who came back to this in great detail. But first, Giuliani, hopefully I'm saying that right, found that, of course, we knew that there were these streaks going across the Earth's sky, and people started to realize that these were, they called them meteors, and they realized they were actually from small pieces of debris falling from space into the Earth's atmosphere. So we finally figured out space was not empty, besides the big objects we could already see. And then, as shown, there were some similarities to those dropping the balls in the mud or other low velocity impact experiments. And this course could explain many of the things that we recognized with craters, including their shapes and sizes and other parts of the craters. But basically, since big objects don't come through our atmosphere a lot, which is a good thing, because otherwise they'd create lots of problems. Mostly these objects were too small, and like the craters we could see on the moon were pretty big. Like these things are miles across, the size of states or even countries. So, and then, what if the crust wasn't hard enough? And so, and there seemed to be a little bit of a volume argument that we couldn't explain yet. And so, and then not all craters, actually a majority of the craters are more circular than this example I'm showing down here, which is very elliptical. And at low velocities, they were almost all elliptical, unless they were coming directly from the top. So, or vertical impact, basically. And so, and since they figured most things wouldn't come in vertically, actually the most common impact angle is about 45 degrees. People were like, well, why are they so circular when there's not that many vertical impacts? And basically, another couple centuries went by, and we discovered that really what it is that velocity matters. So all of these experimentations I've been talking about so far were at a very low impact velocity compared to the velocity that happens actually in space, which is like in the several kilometers per second range. So these are very fast objects, where on Earth, a lot of these, of course, early experiments were no faster than what gravity could do. So they discovered that basically, because of the impact speed and the energy associated with that, unless the impact angle was very low, or less than 30 degrees to the horizon, you would get a circular crater, or a generally circular crater. And then we also started studying like explosions, which was better simulating the high velocity impacts. So what can craters tell us about not only our world, but what's going on in space? And one of the things is because they basically naturally dig holes in the ground for us, and they create high shock and high temperature. This can let us see what's going on underground, and it changes the minerals in the rocks, so we can kind of get an idea of what the physics is going on, and what these kind of impacts do to bodies and the surface. So here again, we see the crater that you saw me and my son when he was much younger standing in front of. And this is, if you're ever in northern Arizona, this is called Meteor or Barringer Crater, and it's open to the public to go view. You can't really walk around it much because they're trying to prevent erosion, but you can go see this crater. It formed relatively recently as these things go. I think about 20,000 years ago. And so primitive humans probably saw this happen. And it's about a mile wide. So it's just a really cool feature of a young impact on the Earth. So the craters can also tell us about the things that hit them, hit the bigger bodies. So on kind of the upper left here, what I'm showing is a chain of craters on a moon of Jupiter. And this was formed by the fact that comets actually break up sometimes when they pass by the sun or by Jupiter. The gravity of those two bodies is big enough to actually break apart a body. So we can learn a little bit about that dynamics. We can learn about the small bodies in the solar system in general and their populations. And then something I use a lot of my work for is shown on the bottom left, which is as a surface gets cratered over time, if you know that rate, you can use that number of craters as shown by the plot on the right that increases with time what the potential age of that surface is. So that's something I focus on. So how do craters tell us? We use a wide variety of data sets to study them. And of course, here on Earth, we can actually go visit them and pick up the rocks and look at them. But in space, we use more different kinds of observations where we'll look in just a plain view as shown by the figure on the left at how their size and how their shape and different features change with their size and how old they get over time. And then on the right side, we can see more just these are more like spectral or even topography images of craters. So when we can't actually go to them, we can use these kinds of things to understand the materials and what they look like. This is actually even remote sensing of a crater on Earth, because sometimes they're so big we can't see even on Earth what they're doing until we get into space. As I mentioned, we started doing experiments which help us understand the craters better and how they form. So up on the upper left, I'm showing a image from an actual, basically large underground nuclear test explosion. We don't do those as much anymore, but when we did, they showed us a lot about how craters can form, just because even though they weren't truly an impact, they created a lot of the same energy. And then in kind of the upper right, that is what's called the NASA vertical gun. It's located in Ames, which is in Northern California. And basically they use that to accelerate smaller objects, as you see in this series of images. So these are usually small marble-sized things up to the impact speeds we can see it in space, that several kilometers per second. And that also can help us, even though it's a much smaller scale, it can still help us understand the what goes on during an impact. And then finally, towards the bottom, just show an example from a numerical simulation, so something people do on their computers, and they've used the experiments and other things over the years to teach the computers how to simulate an impact. And this course allows us to simulate on Earth the big impacts we can't do with the other actual experimentation types. And as I mentioned, what I'm most interested in is understanding how the number of craters change with time and with place, to understand the ages of the surfaces I'm looking at and the impactor populations that are making those craters. So here I'm just in the upper left, I'm showing an example from the actual software I use. It's called JMARS. It's freely available. You can use it to look at images and do crater mapping, do other feature mapping, and they have pretty much every solid body in the solar system that NASA has sent a spacecraft to. And then you use some specialized plots, which I won't go into the details of, but basically all you're doing is plotting the number of craters versus their size in various formats. And this helps you understand how the the distributions of craters, how their numbers change with the sizes, and it can allow you to compute the age of the surface if you know how many craters you need that formed over the billions of years you're looking at, or you can compare it, as in the bottom right plot, you can compare it to actual distributions of small bodies that telescopes have been able to study. So these are actually the shape of what's going on in various populations in the asteroid belt. So get a little bit now into what I actually do. And one of the first things I'll talk about are so-called wet craters on Mars. So water is important to life as we know it, and it can be very important if we want to visit other places like Mars, and it's even greater if we don't have to bring it with us, because that's a lot of extra weight for the spaceships to carry. So the big question for a long time has been, does Mars currently have water and water ice that's accessible? And we're getting to know, of course, much that up at the poles and stuff there is, and they're definitely there. But the easiest place usually to land is closer to the equator of a body. So like a lot of the first Apollo landings were all very near the equator of the moon, because that was just a safe, easy place to land. And the same is true for other bodies. So the question became, is there still ice somewhere at the equator? And if so, is it very deep underground? Might we find some at the surface? But because we can't use other remote, it's not very near the surface, is what we know for sure. And so we needed something that could dig deeper than what most remote sensing can see, which isn't very deep. And craters are one of the features that can do that. And they can dig several meters to kilometers into the subsurface. So what's very interesting, of course, is Mars has what we call these layered ejecta craters. And basically what it is, so this is an image on your left that's showing the ejecta of these craters look more like a mud flow or something like that, rather than what we more typically see, which is called a radial ejecta crater. And we see most these on the moon, and they do also occur on Mars, but it looks like more like rays of material came out, and that's what we expect is for when you impact into dry material. So we can use the idea of these two craters, one forming in wet material, one forming in dry, to try and better understand the distribution of ice near Mars equator. And one of the problems I was specifically considering is when you look at the distribution of these identified craters, either with that layered or wet morphology or the dry morphology, which is red in this image, and the wet ones are blue, you can see that there's a very strong mixture. And on the face value, this would imply that the ice might be really mixed in with dry. It's very patchy, or who knows what's going on. But the problem is there's not really good geological explanation for having such patchy ice under the surface. But in this image, what is missing is time. So are all the red craters older than the blue ones? Are all the blue ones older than the red ones? So that was a project I undertook, was to try and figure out the timing of the formation of some of these craters. And I did a small selection of them because unfortunately measuring these and mapping these craters takes some time. So I had a limited amount of time to work and figure out things, but I did about 70 craters so that we had a good sample. And they were located kind of in these groupings to help us understand both local changes and regional changes. So one thing I'll mention, so to get the ages of those larger craters, what I do is count craters on their ejecta blankets that have formed since those craters formed. And but part of the problem, especially with Mars, is Mars is still an active place, especially with wind and dust movement. So You can have erosion of the smaller craters that formed. You can have deposition of new material on top of them. And so this might change the number. And then you can also have what we call secondary craters, which are craters that form and typically in clusters from the main impact. So basically, some of the ejecta is very fine and comes out as the blanket, but then some of it is still very chunky and it just actually forms new small craters of its own around the bigger crater. And you can see an example of these in the lower left image, where you can see a cluster of very small craters just to the southwest of the main crater. So all of these things can mess up what kind of age you're computing for the crater, and when it formed, it can make it look like a different number than what it actually is. So you just have to be very careful.
So Michelle, could you look at the questions in the chat?
Yeah.
Or are you not able to see them because the screen is taking up everything?
Yeah, I think.
Yeah, we have a bunch of questions. I think it would be good if you could answer them before you keep going.
Yeah, that's fine. Let me stop sharing, I guess.
Or I could read them to you. Wants to know if the faster the meteor, the more material it displaces.
Yeah, that is true. So either the faster or the bigger, because basically what you're doing is adding energy to the problem. And in this case, we're thinking about kinetic energy, which is mv squared. So v being velocity. So yes, definitely the faster, but you could also increase m. So yep.
And then Anish wants to know if the blue dots represent the wet ones.
Yep, that is true.
Pranav doesn't understand why you have what the trouble is.
Yeah, the trouble becomes that when you're trying to understand when something formed, but you may not get the exact, or you may not get the number that you're looking for because the data has been altered over time. So yeah, yep. Yeah, there is a constant in there that I forgot for kinetic energy. I was just doing the variables mv squared. Yep.
So she was just talking about how the kinetic energy depends on m and v, and the half is yes, there is a half to get the correct answer for kinetic energy, but if you're just looking at how things scale, scientists often just look at the variables and not at the extraneous constants that are needed to solve physics problems.
Mm-hmm.
Yes, what is the definition of secondary craters again?
Yeah, because they're secondary craters.
Mm-hmm. So let me see if I can share again. Okay, so yeah, so secondary craters. Let's see.
Now you might want to back up.
Yeah, there we go.
Yeah.
Okay, so when you have the big crater that forms, so let's take this one in the lower left. When you have the big crater that forms, part of why it forms is it pushes, so you have to dig material out of the ground and move it. And so part of that material goes into making what we call the ejecta blanket, which is the more solid circular feature you can see around. But some of that material stays more as chunks of material. And so when those chunks spread out, they actually hit the ground again and form their own little craters, which you can see a few of down in the lower left part of that image. So maybe if you, I don't know if you guys see my cursor or not, but
you can see it. So, but how do you know that those little ones are different than those other little ones that are like above it inside the lines? There's little
so I don't, but one of the typical rules about secondary craters is they don't usually form on the crater's ejecta blanket because they usually go farther. They have more velocity. Now there's possibly a rule where that doesn't apply. Some people have talked about secondaries landing even on the crater itself, but that makes things more complicated even yet. And if you see these purple circles, which are very tiny here, this is actually a group of what I think are secondary craters, probably from another crater that came that's somewhere up in the, northwest of this crater and formed these on top. And so I had to kind of remove them from my study in order to hopefully get a better age.
So basically, a secondary crater is a crater that's made up of particles from another crater.
Yeah. Mm-hmm. Mm-hmm. So, but what makes
They're
them
leftover
potential?
particles, or they're leftover particles, or they're just they're leftover particles from another crater, or like those craters, like they stay in one position.
Yeah, they're kind of left over. So they're basically
Oh,
when material comes out of the crater, it gets spread quite a bit away from wherever that crater is. Sometimes it comes kind of close, like you can see in this one. Sometimes they're very far away. So yeah.
okay.
I see that we have some hands raised and some other questions, but do you want to,
Yeah, I
keep
think,
going through and
I
then-
think people should go back to putting their questions in the chat and mute themselves. And Michelle should keep going.
Okay.
So I
Yeah.
think we all understand this lovely set of images here.
Yeah. Okay. So basically just some quick results from this project were that basically find that the ages didn't help us. They still looked very random. And so what you're seeing here are just some plots of the size of the crater versus its age. And again, red indicates the dry craters and blue indicates the wet craters. And you see they're pretty mixed together, except for maybe what we call young craters, even though they're still up to 3 billion years old. They're still younger than the majority of craters which occur before that time. And you can see that maybe there are more the wet craters forming at larger sizes than at smaller sizes where the dry craters dominate. And these plots down below are just some detailed statistics that went into that effort to make sure what we were seeing here was real. And so they're kind of a way of doing a fancy regression to understand what we're seeing in each of the groups. So we take the data and try to come out with the predictions. And so of interest is the green line, which are these younger craters again, but just all grouped together. And you can see that they're more likely to be radial when they're small than they are when they're big. And basically what this came out to be for us was that there was probably a source of temporarily variable ice. And this might be glaciers that come at the equator when Mars's rotation axis tilts a lot. So unlike the Earth, Mars doesn't have a big moon to help keep its rotation axis stable. So sometimes it can tilt quite a bit. And this can bring ice and glaciers that are currently at the poles to the equator. And then also probably that there might be certainly a deep reservoir of subsurface ice, but that has gotten deeper over time. So it was harder. You needed a bigger crater in order to reach that ice as we've gotten into more modern times. I don't know. Do you want me? It's almost,
Yeah,
I
we
have
have-
another small group, but small project, but I can skip it if we want.
Well, we do have a couple more questions, and we're sort of running out of time. So I think we might just
Okay.
have to wait for the outer solar system until later.
That's fine. Yeah.
Yeah.
So
So
yes.
for example, we have a question from Pranav: do craters help make Mars uninhabitable?
Uninhabitable?
That's the question.
There's been a lot of thoughts about whether craters help habitability or hurt it, and it can do a little of both. So craters, of course, do deposit a lot of energy and a lot of heat. So that can be hard on life if the life doesn't want that much energy. Also, if you have a thick enough atmosphere, it can deposit a lot of stuff in the atmosphere and actually make it colder after a while because there's so much dust in the atmosphere that's blocking sunlight. So maybe you have heard that one of the ideas, and probably the most prominent one right now, for the killing off of the dinosaurs was an impact, a very large impact. This impact is, I want to say, like almost 100 miles across. It's all under the ocean right now, and they thought basically that large impact would at first create a lot of fire, which would destroy the vegetation and other small things, animals that the dinosaurs might have eaten. But then after that part was done, it might have gotten very cold because there was all this debris in the atmosphere that blocked the sunlight. And so then the dinosaurs couldn't deal with the cold either. So there's kind of a joke I have here, a cartoon from Far Side that Gary Larson wrote many years ago about the idea of what hurt the dinosaurs. But and the idea is that the climate change was part of, basically a result of that impact. But at the same time, since the impact creates heat, if you're on a planet that's much colder like Mars, that heat might actually be helpful to life because it might provide some a higher temperature and maybe even more water where life is trying to start or to evolve. And those are good things for life. So, but there's a lot of work out there on that. That was a very brief summary.
Yeah. So you told me how craters on a cold planet could make it more habitable, but is it true that craters can also make a planet less habitable?
Yeah, that was kind of the example I was giving with the dinosaurs here on Earth, is if you get too much heat and too much atmosphere blockage, that can definitely be harmful to life.
Yeah, atmosphere blockage.
Yeah. Basically, it creates constant clouds and that are very thick. And so those constant clouds that are very thick can block too much sunlight from getting to that planet that would then cool the planet too much.
Yes,
Okay, so are there other people that have their hands raised that didn't put stuff in the chat? Can you see them,
I think
Megan?
we still have one more question in the chat before we switch over to hand raising. Gabriel wanted to know, could you speak further to how you calculate crater age?
Yeah, so let me go back to here. So that's what this example is kind of showing, which I flew through pretty quickly. But so what I'm doing is getting the number of craters that have formed on the ejecta of this big crater. And I can plot it up such that I'm looking at the number of craters with their size. And then I can match that to what we think that number should be for a size for a given impact rate on any surface. And so that we call that a chronology function, which is shown by this lower left plot. And the chronology function for Mars has actually been developed from information we got from the moon, because we have sent astronauts to the moon who brought back rocks to the Earth. We actually have areas on the moon that we know the ages of very well from a different technique other than craters. So we can combine the ages we found on using those rocks on the Earth with the number of craters, and then you can create what they call a calibration, or you have points where you have to say that, okay, so if something is 2 billion years old, then it has to have this many craters on its surface, and that's the rate we need to compute ages. So hopefully that helps.
Okay, in the meanwhile, we have more questions that came in. Why do celestial bodies such as Mars and the moon get hit so frequently while the Earth doesn't?
at the moment, they don't get hit any more than the Earth does. The biggest difference is that the Earth has a much thicker atmosphere than either of those other two bodies. So even though Mars has an atmosphere, it's fairly thin. And so when small asteroids or small objects hit a thick atmosphere, they actually burn up, which is why we see shooting stars and meteor streaks, because basically what we're seeing, those small objects burning up in our atmosphere, so they never reach the ground. Now, the bigger they get, the more likely they can get through the atmosphere and cause a crater. And because the moon has no atmosphere and the Mars only has a thin atmosphere, most of the objects make it through to form a crater. And so what we're actually not seeing is that either that the moon or Mars has been impacted more than the Earth, but just that the moon and Mars have retained more of the craters that have formed over their surface lifetime. And so that's the other difference about Earth, is that the Earth has plate tectonics, which recycles the crust. And so the Earth has just hidden just as much as those two bodies, but we've lost a lot of the surface over time due to the plate tectonics, the original Earth surface. So we see more new surface here on the Earth than any other solar system in the body, other than a Jupiter moon, but that's a whole other problem.
Okay, well, now we're definitely running out of time, so I think that we're gonna have to end, but these are all great questions. And
Yeah.
and I think if you have more, you should write directly to Dr. Kirchoff. She has her
Yep.
email address here.
Yep. And here are two books, academic books that have been written on the process of impact cratering. And so maybe you can find them maybe at a local library or at your university library, and they can tell you a lot more too in detail. But yes, I'm happy to take your email questions as you think of things, and I might just stick around and put some things in the chat as long as we're going.